Today I'll be talking about the Global Media Network. I am at the Department of Physics and Astronomy at the University of Western Ontario in Canada. And why do we need a planet-sized scientific instrument? That's how I call the Global Media Network. Well, the truth is that there are some very unique events that occur in the sky and that can't be really observed in a traditional way, in a traditional kind of regional, local way. Such as very rare meteor showers. Sometimes they might last, only 10 minutes, half an hour, like let's say alpha inosirids or something like that. And also we have meteor dropping fireballs. And when we really do have a very interesting event, it is important to have a high quality observation that can be calibrated, so you don't have to, try to calibrate dash cams, security camera videos, and that stuff. So that's basically the whole point behind the network. Have something that is low cost, simple to maintain, and also have transparent methods that every amateur astronomer worth his salt should have on his house, right? So in practice, we have a Raspberry Pi microcomputer that's connected to a camera, and that's kind of basically the whole system. So the network itself started in 2018, and right now we have over 200 people, over 450 cameras in 30 countries. It's a mix of amateurs and professional astronomers. And the network itself processes about 400 terabytes of video data every night. Everything is privately funded and maintained. We really don't have any official funding, and I like that. It makes the development quicker. There's less bureaucracy. I have more time for science, and that's great. And it seems to be working out. So let me just tell you something about the people who actually participated in the network. For example, we have people who never before did anything in meteor astronomy. There's one amateur meteor club in Albuquerque, New Mexico, and they were actually the first ones to start installing Global Meteor Network cameras en masse, and now they have over 30 cameras there. On the other hand, actually right next door in Arizona, the Lowell Observatory operates several sites, and they're using these cameras to support their National Science Foundation grant. They're doing some crazy stuff with asteroids and meteors, and I think that's really cool. And also in the UK, Global Meteor Network is trying to bridge the gap between many different networks there. Especially after the Winchcombe event, we saw a large rise in installations of Global Meteor Network cameras, and now there are over 80 cameras there. Generally, people that we get, I was really surprised, we don't really have a lot of people who were doing meteors before, but we mobilized a lot of new people, and most of them seem to be other professional software developers, some are engineers. So we do have a lot of talented people in the network. And me as a coordinator, the way things are set up, I have almost zero work after the initial setup and calibration. Once you set it up, I check the data quality and I kind of add it to the pipeline, and that's it. So after that's done, I make sure that good quality data is coming in, and that's it. I have more time to do science. So in terms of what we actually get, and what we actually use, we also use the IMX291 IP cameras. We think they're great. We use mostly 3.6 millimeter lenses that give a field of view of about 90 times 45 degrees. And these are CMOS sensors. And what's great about them is there's no blooming. Of course, once they're close to saturation, the photometry isn't great. But I mean, for fireballs, the photometry, we can't really get it saturating anyway, so who cares? In terms of the cost, we work with a private partner that builds plug-and-play systems. If you want a system, they will sell it for you for 400 euros. If you want to build one yourself, we have a list of parts, instructions that's actually built and maintained by a lot of amateur astronomers, and they like the building cameras and stuff. And the whole cost is around 200 euros. The software itself is open source, so you can find it on GitHub. The methods are completely transparent, and we caught quite a few interesting events. One of which was the Winchcombe event, and funnily enough, it was caught by a camera that was installed 2 days before the event, and it wasn't really properly focused yet. You can kind of see on the right side of the image that it's not perfectly in focus, but that was really lucky. And what's great about these is that we can resolve the wake, the beginning of the fragmentation, and we can resolve individual fragments, mostly at the end of the trajectory, which is really useful if you want to determine the mass distribution, the strewn field, dynamic mass, et cetera, et cetera. We also do install different types of cameras, but that's mostly for meteor work. It ranges from these wide field sensors, wide field lenses to, let's say, 8, 16 millimeter. We also do some experiments with like a 50 millimeter lens, very small field of view. We generally do not install all sky cameras. We just find that the quality, especially on these lower resolution sensors, isn't really that great or useful for any accurate trajectory analysis. In terms of the data format, this project kind of grew out of what was done in CAMS. So it's mostly based for fainter meteors. So we have this, what's called a 4-frame temporal pixel format, where you take like a stack of 256 frames and just find the maximum value, average value, standard deviation of every pixel, and also you encode the frame index of the maximum value when the maximum value happened as like a image brightness, and then you can kind of compress this huge amount of data into something smaller. This works great for fainter meteors, doesn't work great for fireballs, as you can see here on the right side of the right-hand side, this E inset. When you reconstruct fireballs from that, they look really bad. So we have an automated real-time fireball detector, which extracts raw frames of fireballs, and that's basically what you've been seeing on the previous slide, those little cutouts of fireballs. And the measurements that are done are in the global fireball exchange format that Jim Rowe was going to talk about in I think in the next talk. Now, the main workhorse of the package is the SkyFit program. It's basically just a way to ingest any type of meteor data that can be in video files, images. It supports Freepont files, identifiable network stuff, even dash cams. And you can calibrate it using several different methods, compensate for refraction, many different things, and have a really high quality calibration. You can also do photometry. Just an example of what we usually get with our 3.6 millimeter lenses. So we operate cameras at 720p, and with that we get an average fit error, astrometric error of about 0.8 arc minutes. That varies from, let's say, 0.7 in the best case to about 1 arc minute, which translates to about 22 meters to, let's say, maximum 100 meters at a very, very long distance. Let's say you have a fireball 300 kilometers away. And in terms of the calibration, at least for fainter meteors, we do automated recalibration when we recalibrate the pointing every 10 seconds. And what we notice is that you can have a huge pointing drift throughout the night, up to 10 arc minutes. And keep in mind, our astrometric precision is about 10 times lower than that, or better than that. We also recalibrate the photometry automatically because sky conditions change, but that's not really used for fireballs, again, only for fainter meteors. As I said before, we can ingest other types of data. Here we have a desert fireball network camera that we operate here in Ontario. And we can calibrate it, again, very accurately, down to about half an arc minute. And we can combine all different data sets to produce one quality trajectory solution. And that's what we've done with Winchcombe. I'm going to talk about that later. Well, actually, I'm going to talk about it now. So Winchcombe, again, it dropped over 500 grams of very pristine carbonaceous chondrites. What it is part of the effort, the work is still ongoing, but I took different measurements from the GMN, from DFN/UK fall. There's also the UK MON network. They operate the UFO software package, and there's also FreePond. And I combined all of that in SkyFit, did individual measurements, calibrations, and I got the fit to be about to within 50 meters, again, depending on the measurements and things. But what's really important here, that I really had to have access to raw data and had to manually very careful to reduce all the observations, and sometimes it's not just about it's also about you have to guarantee tracking the same features and fragments on the image. We also have one guy who's actually a spectral scientist. He doesn't really do much with meteors, so he installed a grating, and we actually got the spectrum of Winchcombe. And as I said, we can also do dash cam calibrations, although that's really, really hard. We prefer not to do it, but it can be done, and we're currently doing this for the daytime meteorite dropper that happened in February 2020 in Slovenia. And what you can do is you can kind of very accurately determine the position of certain key points on the image, and then invert the distortion. You can invert the actual location of the, let's say, the vehicle to within even a couple of centimeters. The software package allows all that stuff. And again, you can get the measurements of the actual trajectory accuracy to within less than 100 meters, no problem. Now, in terms of the actual measurements, as I said before, we do everything manually. And I think the reason is simple. If you just look at what's going on at the beginning, it's actually easy. Before you start seeing any wake or any fragmentation, you can just centroid this part. But once you get some wake, it's really hard to determine where the real head of the fireball is. And once you have some flares, you really have to kind of do it almost iteratively. And of course, at the end, as you can see here, we often see several discrete fragments at the end. So if you just do a centroid on that, you're just completely disregarding whatever is going on, this whole complexity of the phenomenon. What this allows is very accurate determination of the final deceleration, i.e. dynamic mass. And then if you do that for several fragments, you can kind of very accurately get an understanding of the mass distribution of the fall zone, right? In terms of the actual accuracy that we get, what's interesting is that for a lot of events, we see that fragments starts kind of get a transverse velocity after a point of fragmentation. And generally the accuracy is really good within, let's say, 50 or so meters, even lower. But for these final moments when this one singular fragment, which stopped fragmenting in a significant way and doesn't really have a wake, you can pick it really accurately. And if you just take those final moments, you can get the location of the final fragment down to, let's say, magnitude +2. When it decreases in brightness, down to a precision of about 10, 20 meters. Really depends on the event. The way then we compute the orbit is we just kind of exclude this last part, take the initial part, and run it through the Monte Carlo solver, which estimates the uncertainties. So here, this is kind of a 3 sigma noise added solution. So I would say this is kind of the upper limit, and get radiant solutions down to, let's say, 0.1 degree. I think this is actually even better in practice, and velocity solutions that are, I would say, several tens of meters per second in accuracy, because these fireballs didn't really significantly decelerate until, let's say, 60 kilometers or so. But because these cameras are sensitive, we can just see them starting at, let's say, 90 kilometers sometimes, no problem. As for the software, methods are transparent. Everything is on GitHub. If you want to see how we're doing things, it's there. And the reason why I like doing this is because I might have a bug in the code, and when other people use it, they say, oh, you see, like, this is not good. And that happened before. For example, like Hadrian noticed that I was not plotting the location of the vernal equinox correctly. So I fixed that, I think, about a month ago. So it helps everyone, but it also helps me because I don't have to debug my code. Other people notice things too. And in terms of the data policy, now this is something that's very important that people understand, is that to understand how the GMN works, we are kind of like imagine Sonatico, which provides a software, and combine that with Edmund. So we provide the software, people operate the cameras, but they own the data. So we have kind of sub networks or people who are a part of, let's say, CAMs or UKMON or whatever, they're using RMS data and contributing to those efforts. We have no problem with that. Absolutely no problem. But they own the data. They decide what is done with the data. The only thing that is done, though, is that the measurements of fainter meteors are uploaded to the central server. And we're just doing it a very simple way. We just have like SFTP that's transferring some text files, nothing crazy. The reason why it's so simple is kind of the time horizon of this project is about 20 years. So I want to make sure that the technology that I'm using now will still exist in 20 years. So if we look back 20 years, a lot of the stuff we use now didn't exist. But I'm fairly confident that FTP and SSH will exist in 20 years. In terms of how the data is handled, the Fireball data is handled, the Fireballs are reduced by advanced participants. And sharing the Fireball data is really a matter of agreement with station operators or networks. So if you have, let's say, a network in your area and you want to access the data or something, you have to talk to the people who are actually operating the cameras. I have very little influence in what's going on. As an example, Pavel sent an email to Damir in Croatia, who's operating cameras that cover some parts of Central Europe. And he asked, oh, you have cameras here in our territory, what's going to happen now? Damir said, no, we're completely open for collaboration. We respect everything and there's no problem. There's also an amateur in Prague who operates a camera who's very open for collaboration. So you really have to talk to people on the ground. I have nothing to do with it and I don't want to have nothing to do with it. I'm just interested mostly in faint meteor data, and if really some amazing Fireball happens, I will try to find time to do something there to help out. And of course, strewn fields, well, they can be kind of contentious. People don't want to share that, and I completely understand that. They're kept private to prevent meteorite hunters. Yeah, that's the way to do it. As for the orbits of fainter meteors, they're automatically computed, available online within 24 hours. They're a very liberal license. So if you're interested in fainter meteors, that's all available. Fireballs, on the other hand, require more work.
You have 3 minutes left. Just for
Thank you. And what can the GMN do for you? Well, again, all the tools are freely available, open source. And we also have some video tutorials on how to use them, how you can produce this high quality data. Now that takes some time, takes some practice, but a lot of amateur astronomers were able to do it, and now they make their own plates and calibrations and everything, and even reductions, and I'm really, really happy with that. As for further data availability, again, it's all about some sort of collaboration or funding if you want some access to data for certain amateurs or something. It's really, I left this part kind of undefined and in the hands of people who actually produce the data, so I can just avoid any issues. One of the reasons why we're here today is to discuss machine learning ideas. Well, one obvious idea is how do we automate this reduction? How do we mitigate this complexity that Fireballs have? We need some better idea to reduce them instead of some simple centrating or point spread function fitting, something that can handle flares, multiple fragments, which again can help estimate the final mass distribution on the ground. Maybe something to do with the saturation correction, but I'm not really hopeful there. Although in the GMN we do have an algorithm for automatic recalibration, it would be great if we could have something where it's like, oh, here's the image, calibrate it automatically and just do the reduction automatically, and then produce the measurements that we can check instead of doing all the hard work manually. And finally, one very interesting thing is to determine the flux and the origin of, let's say, centimeter size or larger bodies. And again, to do the fluxes, you have to have very accurate estimations of the collection area, cloudness, sensitivity loss, blah, blah, blah. And that's something where I think machine learning could really help. Well, thank you for your attention. Do you have any questions?
Thank you very much for this nice talk.